Today I thought we could take Google's new product called NotebookLM out for a spin and see how well it does on some of the publications that we've produced at the Atlantis project. So it seems pretty approachable. We have to create a new workbook. I've already chosen some files to upload to make this easier. I did learn that files have to be stored as a PDF or many other formats, but they can't be Word documents. And you can load many of them at once. So let's do that. You can see it's fairly quickly processing all these files. So that did not take very long. And I guess we can ask it questions now. So let's try, well, what is a variable pitch screw launcher? We'll see how it does. Oh, seems to be taking a while. No answer yet. Oh, here it goes. See how it did. Wow, quite an essay here. A variable pitch screw launcher is a type of electromagnetic launch system proposed as a more cost-effective alternative to traditional chemical rockets for space launch, particularly for missions beyond low Earth orbit. Here's a breakdown of its key characteristics and advantages. Variable pitch screws. The core of the system involves two long counter-rotating screws housed within an evacuating tube. The key feature is the variable pitch of the screw threads, which start with a fine pitch near the beginning of the launcher and gradually become coarser towards the exit. That's perfectly accurate. Magnetic coupling. Launch vehicle sits on the sled that is magnetically coupled to the screw threads. As the screws rotate at a constant speed, the variable pitch causes the sled to accelerate down the length of the tube. Think of it as surfing on a mechanical wave generated by the rotating screws. Pretty accurate again. Electromagnetic propulsion. Instead of relying on rapidly switching electromagnets like coil guns or rail guns, okay, well, there's a mistake right away. Rail guns do not rely on rapidly switching electromagnets, so it kind of lumped rail guns in with coil guns incorrectly here. But let's continue. Instead of relying on rapidly switching electromagnets like coil guns, the variable pitch screw launcher employs linear active magnetic bearing technology. The magnets are mounted on actuators that allow them to adjust their position and maintain constant coupling distance with a change in geometry of the screws threads as the sled accelerates. Okay, pretty good. Advantages. This design offers several advantages, most notably its cost effectiveness. The capital cost of a variable pitch screw launcher is proportional to the square of the exit velocity. Now here you've got kind of a formatting issue, so it's using some kind of markup language. Instead of saying v squared, it's saying v sub, or I guess, yeah, whatever sub stands for. Super subscript, I guess, superscript. The v superscript 2 is really v squared. That's a little bit hard to read. Making it more economically viable for high-speed launches compared to traditional mass drivers or rockets, whose costs scale with v cubed or exponentially, respectively. Additionally, the system avoids the challenges of high-speed switching electromagnets, potentially leading to greater efficiency and reliability. Good point. Cost estimates. A parametric model estimates the capital cost for a human-rated variable pitch screw launcher capable of accelerating a 21,181 kilogram vehicle to 11,129 meters per second at $32 billion in 2024 US dollars. The estimated operating cost for accelerating payloads to orbital velocity is around $1 per kilogram. A little bit weird because what happening here is they're mixing a cost estimate for a system that was designed to send payloads onto a Mars transfer orbit with operating costs for a system that was designed just to go to orbit. So mixing these numbers isn't the smartest thing to do, but both those numbers do exist in the various documents that they uploaded. The sources suggest that once the infrastructure is built, the cost per launch becomes significantly lower than traditional rocket launches. This is definitely true. Components in operation. Evacuated tube. The entire system is housed within an evacuated tube to minimize air resistance and enable the vehicle to achieve high speeds without significant aerodynamic drag. Correct. Launch sled. The vehicle is mounted on a launch sled that rides along a central maglev rail within the tube. This magnetic levitation eliminates friction between the sled and the rail, further enhancing efficiency. Screw segments and motors. Each screw is composed of multiple segments, each powered by electric motors that spin them up to operational speed. Flywheels within each segment store rotational energy and transfer it to the screw segments during launch, ensuring consistent rotational speed and reducing the reliance on high-powered energy storage systems. Yeah, it's pretty good. Grapplers and magnets. Actuators on the sled control grapplers, magnetic pads that couple to the screw threads. These magnets are arranged in a homopolar configuration to minimize energy loss due to eddy currents. Also good. Ramp and elevated tube. At the end of the mass driver section, the sled travels up a ramp, typically built on the side of a mountain, to gain altitude and direct the vehicle upwards. An aeronautically suspended extension of the evacuative tube, potentially supported by cables or other structures, further extends the launch path and reduces the vehicle's exposure to the atmosphere. Yeah, this is pretty good. The potentially supported by cables or other structures is probably referring to the paper where the launch tube was supported by the tethered ring. That's kind of a vague reference to that paper, without mentioning the tethered ring. Further considerations and challenges. Atmospheric drag. While the evacuated tube minimizes air resistance within the launcher, the vehicle still encounters atmospheric drag upon exiting. Several solutions have been proposed, including using a rocket engine for short bursts to maintain speed and manage thermal loads during this phase. It's kind of true, but this doesn't really explain how the rocket engine is used. The idea behind the rocket engine is that its cryogenic propellants can be circulated through the nose cone to actively cool the front part of the spacecraft, as well as cooling the nozzle and combustion chamber of the engine itself. So that was one of the techniques that was mentioned in early papers. The other reason to use the rocket engine is to prevent the atmospheric drag from slowing the vehicle down as it leaves the atmosphere, maintains its speed. All right, technical complexity. Developing a full-scale variable pitch screw launcher presents significant engineering challenges, particularly in terms of material science, magnetic coupling systems, and maintaining price alignment and control over long distances. So I don't know if I mentioned any material science concerns. The whole architecture is designed to use fairly readily obtainable materials such as steel and electromagnets. There's no superconductors, there's no super materials like graphene or anything like that in this design. So it's very easy to build from a material science point of view. So I don't think that it was appropriate for this software to mention problems or challenges with material science. Magnetic coupling systems, I think that's more of a fair statement. There's a lot of magnetic coupling involved in this technology and maintaining precise alignment and control over long distances. I don't actually think I mentioned that, so this is an example of the tool showing some sort of real engineering intelligence that realized that this would be a challenge to have such a precise alignment over long distances. Mind you, there are lots of other technologies that manage to be pretty straight, such as the rocket sled tracks that they have at, I think it's the Army maintains them, or the Air Force. All right, next section is elevated tube support. Supporting the extended evacuated tube at high altitudes requires innovative solutions. While drones or balloons can provide short-term support, long-term solutions may involve inertially supported active structures or other advanced concepts. That's a pretty good summary. I think I mentioned that at the end of my last presentation. I don't really like the idea of balloons, and I'm sort of not too happy that it suggested balloons in there. I do think that drones or some other form of aeronautic support makes a lot of sense, and the long-term solutions involving inertially supported structures are something I also believe in. So that's pretty good. All right, current status. As of the latest information available in the sources, 2024, the variable pitch screw launcher is still in the conceptual and early development phase. Researchers are actively working on refining the design, conducting simulations using digital twins, and building small scale prototypes to test and validate key aspects of the technology, all quite accurate. If you'd like to learn more about the specific considerations, cost calculations, and potential applications of the variable pitch screw launcher, I recommend referring to the sources, and they list the sources for more in-depth information. It's pretty good. All right, let's see what the next question was. This question, I think, was one that the tool actually suggested, so I clicked on it. What is the estimated cost of a human-rated variable pitch screw launcher capable of accelerating 21,181 kilogram vehicles at a speed of 11,129 meters per second? And the answer it gave was the estimated capital cost of a human-rated variable pitch screw launcher capable of accelerating 1,181 kilogram vehicles to a speed of 11,000 meters per second is $32 billion in 2024 US dollars. This estimate comes from a parametric model developed by the Atlantis Project, as described in their paper, Revolutionizing Space Launch, the Economic and Operational Benefits of the Variable Pitch Screw Architecture. What the source doesn't explicitly detail is how they arrived at the 32 billion figure. It does mention that the model considered various factors, including the length of the launcher's submerged section, which is 774 kilometers, an underground ramp of 83 kilometers, and an aeronautically elevated section of 122 kilometers. The cost of materials for the screws, brackets, rails, and evacuated tube, the cost of motors and tunneling, the cost of the aeronautic lift system. The source emphasizes that the model employed conservative estimation techniques. For example, they determined the cost per meter of the elevated tube by analyzing Spirit Aerosystems 2023 fuselage production data. Similarly, they factored in material costs and manufacturing expenses based on the launcher's digital twin. Model calculations and underlying assumptions are available on GitHub, allowing for further scrutiny and analysis. Yeah, that's a pretty good answer. A lot of extra detail in the answer that beyond what I think the person was just asking, which is they're looking for the $32 billion. So it embellished and it did a good job of it. All right, the next question. Do passengers in the spacecraft need to wait in the vehicle while the tube is drawn down to a vacuum? So this is a question that I found looking at comments on the video of the presentation that I gave at the International Space Development Conference, I think in May of 2024. I also had a typo here, and it didn't seem to be a problem for this NotebookLM tool. The answer it gave is, it is unclear from the sources if passengers would need to wait in the spacecraft while the tube is drawn down to a vacuum. The sources primarily focus on technical aspects and economic feasibility of the VPSL system, without delving into detailed operational procedures like pre-launch preparations. However, the sources do mention the presence of airlocks, or fast-acting doors, at the end of the evacuated tube. These airlocks serve to maintain the vacuum within the tube while allowing the spacecraft to exit. This suggests a possible scenario where the spacecraft is loaded and sealed in the tube while it is still at atmospheric pressure. Then the tube is evacuated. Once the desired vacuum level is achieved, the airlock doors rapidly open, allowing the spacecraft to exit and begin its launch. Okay, so this is really bizarre. I don't think any engineer who'd read these papers would say something like this. It's kind of strange to say that after you retrieve the vacuum level, you rapidly open the doors and then the spacecraft begins its launch. It sort of shows that the NotebookLM tool doesn't really understand the engineering of this design, and it's sort of just making stuff up based on piecing together bits of text that it's read. So here's some evidence that the tool doesn't have the kind of engineering knowledge that an engineer would have, and haven't got a mental image of what's actually going on in this launcher. Although from all the other text that's been written, you might think it does. All right, this hypothetical sequence implies that passengers wouldn't need to be on board while the tube is being evacuated. However, without explicit information from the sources, it remains speculative. It's important to note that the sources prioritize the technical and economic aspects of the VPSL system rather than passenger experience or operational logistics. Therefore, further research or clarification from the source authors would be needed to definitively answer your question. So basically, it took a crack at coming up with a theory, and I don't think it did a very good job on this one. So that's pretty interesting finding for the tool. Just for reference, the way it works is that the tube is drawn down to a vacuum once, and it's maintained at that vacuum for the life of the device, much like the beam tubes that are used at LIGO observatories, the gravitational wave observatories. They were drawn down once when they were first constructed, I think maybe 25 years ago, and they've maintained an atmospheric pressure of 1 trillionth of an atmosphere ever since. And if they ever need to make any changes on the instruments, they have an airlock at the ends of the tubes that they can use to service the instruments. But the main portion of the tube is maintained at a vacuum, a very, very low vacuum, um, and it stays there forever. And it's a similar idea for this evacuated tube. We would evacuate it once, and then we use an airlock at the beginning to get in and place a spacecraft inside the one end of the launcher. And then it travels down the launcher and exits at the other end through a second airlock with the fast acting doors. So to answer the question correctly, the passengers do not need to wait for the tube to be drawn down to a vacuum. They only need to wait for the airlock chamber to be drawn down to a vacuum, which doesn't take very long. All right, the next question is, can you point out the differences between this and spin launch? It probably also came from, I'm not sure where this question came from. It might have come from YouTube, we'll see. Anyway, here are some of the differences between a variable pitch screw launcher and spin launch. Launch mechanism, variable pitch screw launcher. This system uses two counter-rotating screws within an evacuated tube. A launch sled carrying the vehicle is magnetically coupled to the screw threads, and the variable pitch of the screws accelerates the sled down the tube. This design allows for gradual acceleration and avoids the use of rapidly switching electromagnets. Okay, that's accurate. Spin launch. Spin launch uses a centrifuge to spin a projectile containing a payload to very high speeds within a circular chamber. Now, it mentions here that no source is provided, and it's going off of general knowledge on spin launch, and so that's true. I didn't provide any information on spin launch in the documents that I uploaded to the NotebookLM. Once the desired speed is reached, the projectile is released and launched vertically through an outlet. Pretty much accurate, if you know spin launch. Acceleration profile, variable pitch screw launcher. This system provides a constant acceleration profile throughout the launch. This is advantageous for payloads and potential passengers as it limits the g-forces experienced during acceleration. True. Spin launch subjects payloads to very high g-forces during the rapid spin-up phase within the centrifuge chamber. This limits the types of payloads that can be launched using this method. That's also accurate, so it's quite good. Payload capacity and destinations. Variable pitch screw launcher. The system is designed to launch relatively large spacecraft, potentially including crewed vehicles, to interplanetary destinations like Mars. Sources mention payloads of 21,181 kilograms and propose using the VPSL to establish crewed outposts on Mars. Spin launch. Spin launch is currently focused on launching smaller payloads into low Earth orbit. Again, this disclaimer about no information on spin launch. The company aims to eventually scale up its technology for larger payloads and higher orbits. Infrastructure and cost. Variable pitch screw launcher. This system requires extensive infrastructure, including a lengthy evacuated tube, potentially several hundred kilometers long, a ramp built on a mountainside, and an elevated tube extension. The estimated capital cost is in the tens of billions of dollars. Spin launch. Spin launch's infrastructure primarily involves a large centrifuge chamber and a launch tube. I, I don't know if they have much of a launch tube, so that might be inaccurate. They have a little short tube at the side of the centrifuge, but it's potentially misleading. While still capital intensive, the overall footprint and costs are expected to be lower than the variable pitch screw launcher. That's probably true. Technical maturity. Variable pitch screw launcher. This technology is still in the early stages of development. Researchers are working on simulations, small scale prototypes, and refining the design. Spin launch. Spin launch has made more progress in terms of testing and development. Again, this disclaimer. They've conducted suborbital test flights. I wouldn't say they're particularly suborbital, but it's a bit of a stretch. And secured partnerships for commercial launches. I don't know if that's true. Maybe they have. I suspect they have not secured serious partnerships for commercial launches yet because not to orbit anyway. Maybe for some suborbital test launches that something like a sounding rocket would do. In summary, the variable pitch screw launcher and spin launch represent distinct approaches to space launch, each with its own strengths, limitations, and stage of development. The variable pitch screw launcher aims to provide a more cost-effective solution for large payloads and interplanetary missions, while spin launch focuses on smaller payloads and leverages a different launch mechanism with a potentially faster development timeline. Okay. Next question is, how low a vacuum is needed inside the vacuum tube, and how difficult is it to achieve such a vacuum in a long tube? All right, so let's see. While the sources describe the need for an evacuated tube, they don't specify the exact vacuum level required for the variable pitch screw launch system. However, they do provide some clues and comparisons that can shed some light on this aspect. Reference to existing vacuum technology. One source mentions that a vacuum level of 10 to the minus 9 torr, similar to that maintained in the 4-kilometer long tubes used in particle accelerators, is achievable with current technology. Now, this is probably a little bit of a mistake. I think the 4-kilometer tubes used are for the gravitational wave observatory, the LIGO observatories, and not for particle accelerators. I believe particle accelerators such as the Large Hadron Collider at CERN actually go to much lower levels of vacuum than this. I think this is probably the vacuum level that's being used for LIGO. Now, I don't think I connected those particular beam tubes with this in any of the material that I uploaded, but it was mentioned in the tethered ring. Oh yeah, it's down here. So the source uses this comparison while discussing power losses due to air friction in the tethered ring's evacuated sheath. This suggests that achieving and maintaining such a vacuum level, even in long tubes, is within the realm of engineering possibility. Yeah, so that's a pretty good inference, I guess. It's not directly about the variable pitch screw launch system. It's about the tethered ring, but yeah, it's a pretty good find, I think. So that was a good answer. Emphasis on minimizing air friction. Multiple sources emphasize the importance of minimizing air friction to reduce drag on the launch vehicle and prevent energy losses. This implies the need for a considerably low vacuum to reduce the number of air molecules inside the tube and minimize their interaction with the vehicle. Focus on technical and economic feasibility. The sources primarily focus on demonstrating the VPSL system's technical and economic feasibility. I'm not sure what this has to do with the level of vacuum, but let's keep going. They highlight how the technology addresses the limitations of traditional launch methods and provide cost estimates for various components. However, they do not go into detailed engineering specifications like the precise vacuum level. Okay, I guess they're saying that that wasn't the focus of the material that was uploaded to it. Challenges of maintaining a vacuum in a long tube. Outgassing. Even with high quality materials, some outgassing from the tube's inner surface and components is inevitable. This can gradually increase the pressure inside the tube over time. This is true, but I don't think it's in the material I uploaded. This is general knowledge that it's sharing with us. Leaks. Sealing a long tube to maintain a high vacuum level is challenging. Microscopic leaks can significantly impact the vacuum and require sophisticated detection and repair methods. Possibly true. Cost. Achieving and maintaining a very high vacuum level in a long tube can be expensive. It requires powerful vacuum pumps, specialized materials, and ongoing monitoring and maintenance. Well, I don't know about this. I know that the LIGO observatories are using stainless steel tubes that are spiral welded. It's a very similar technology to what they use to build, for example, the towers for wind turbines. They're also, some of them are also spiral welded, and a lot of pipelines are spiral welded steel. So it doesn't require specialized materials. The vacuum pumps that are required are there's a whole pile of different vacuum pumps. Some of them are fairly cheap and don't go down to very low pressures. Other vacuum pumps are more expensive and get you lower pressures. But they're not particularly powerful machines. There's more it doesn't take a lot of power to get a vacuum. It's something to do with the architecture of your vacuum pump, like what kind of technology is used to achieve the vacuum. But they're not necessarily high power devices. And ongoing monitoring and maintenance, I suppose that's possibly true. All right, considering the factors mentioned above, it's possible that the required vacuum level for a VPSL system would be on the order of 10 to the minus 6 to 10 to the minus 9 torr. This range represents a significant reduction in air pressure compared to atmospheric pressure, approximately 760 torr. That's very helpful that I put that in there, and is achievable with existing vacuum technology. However, the exact vacuum level would depend on various design factors such as the desired launch speed, vehicle aerodynamics, and acceptable levels of air friction. It's important to remember that the sources you provided don't explicitly state the required vacuum level. Therefore, any conclusions drawn are based on inferences and comparisons to existing vacuum systems. Further research or information from the sources authors would be needed for definitive answer. So that's this isn't too bad. Basically, this assistant has done its best to make a guess at the amount of vacuum required. I actually independently did make an estimate that you would need about 5 pascals. So if we did a conversion here from pascals to torr, we get 0.037 torr. So the number it came up with is 10 to the minus 6. So that's quite low compared to what I think it's actually needed, which is about 0.037, I think it said. Yeah, 0.037, which is 10 to the minus 2. It's really enough vacuum for this to work, in my opinion. All right, next question. Would Starship make VPSL irrelevant? Okay, while sources don't directly address this question, they offer insights into the potential impact of Starship on the relevance of VPSL. Here's an analysis based on the provided information. Starship's limitations despite reusability. The sources acknowledge Starship's goal of full reusability and its potential for high launch cadence. However, they argue that Starship's reliance on chemical rockets is still subject to the limitations of the rocket equation. This means that even with reusability, Starship's cost per kilogram to destinations beyond low Earth orbit will likely remain significantly higher than what VPSL aims to achieve. VPSL potential for transformative cost reduction. The sources emphasize that VPSL's unique launch mechanism, which avoids rapidly switching electromagnets and propellant, allows it to achieve a cost per kilogram scaling that's proportional to the square of the velocity, v squared, rather than exponential like rockets. This suggests that VPSL could potentially reduce the cost of launching payloads to destinations like Mars by orders of magnitude compared to traditional rockets, including Starship. For instance, one source estimates that sending a payload to Mars using VPSL could cost as low as $1.85 per kilogram, while traditional rockets are estimated at 1.2 million per kilogram. Okay, this is a bit misleading because this particular source that they're referencing here was talking about the operating cost, basically the cost of the electricity required to launch per kilogram to launch payloads, and not it didn't include the capital costs or the other kinds of operational costs for the technology. So this number is misleading, and I think there's enough information in the papers for it to know that it should not have made that comparison. it's not a fair comparison. The actual capital cost is the actual cost per kilogram. If you factor in amortization of the capital cost, is significantly higher, probably in the hundreds or even thousands of dollars per kilogram to go to Mars, but still significantly cheaper than 1.2 million per kilogram. Even accounting for potential variations in these estimates, the difference in magnitude highlights VPSL potential for disruption. Yeah, that's true. Focus on infrastructure and long-term vision. The sources advocating for VPSL and similar infrastructure-heavy concepts highlight the need for a long-term perspective and significant upfront investment. They argued that while projects like VPSL require substantial capital expenditure, their potential to fundamentally change the economics of space access justifies the investment. Yeah, that's true. In contrast, Starship, while aiming for usability and high launch cadence, represents an incremental advancement within the existing paradigm of chemical rockets. Absolutely accurate. Considering these factors, it's unlikely that Starship's development would render VPSL irrelevant. Even with significant cost reductions, Starship's inherent limitations as a chemically propelled rocket system suggest that VPSL could still offer a more economically viable option for large-scale space exploration and activities requiring frequent launches to destinations beyond low Earth orbit. However, it's important to note that both Starship and VPSL are still under development, and their ultimate success and impact will depend on various factors, including technological advancements, funding, and market demand. So that's a pretty good answer, I think. I didn't see too many mistakes in there other than the $1.85 per kilogram being a little bit misleading. I suppose if you did enough launches that the capital costs were amortized significantly, yeah, then you might get to those certain numbers, but that's a ways off. Okay, let's go to the next question. Is the screw spinning or do the grapplers move? Okay, this question came from the comments on the YouTube video. Both the screws and the grapplers move in the VPSL system, but they move in different ways to achieve acceleration. The screws spin. Each screw segment is equipped with electric motors that spin it up to a high but constant rotational speed. This rotational energy is then transferred to the launch sled, which carries the vehicle. Perfectly accurate. The grapplers maintain magnetic contact and adjust their position. The grapplers are attached to the sled and use the magnetic pads to couple with the screw plates. As the screws spin, the grapplers surf along the variable pitch threads, pulling the sled forward. Interaction is magnetic, meaning there's no direct mechanical contact between the grapplers and the screw threads. This is similar to how a magnetic bearing works. This is very good material. This is well written. To accommodate the changing pitch of the screw threads as the sled accelerates, the grapplers are mounted on actuators that allow them to adjust their position and maintain optimal coupling. The sources also mentioned that the linear AMBs, active magnetic bearings, that control the grappler's position are made up of discrete segments that can detach and reattach as needed to follow the screw's geometry. So this is a bit inaccurate. Active magnetic bearing technology is used in the magnetic pads in the sense that there is a sensor that measures the gap between the magnetic pad and the metal that it's attracting, and it will adjust the strength of the electromagnet based on the distance across that gap. So if the magnet starts to move closer to the metal and the gap gets too small, the electromagnet will back off and reduce its power so that it can pull away, and vice versa. And the opposite is true. If it gets too far away, the gap gets too large, the controller will increase the current to the electromagnet and pull it closer again. So this is how active magnetic bearings work. Active magnetic bearings are not used to control the grappler's position exactly and move them around, which is what it seems to be implying here. Okay, next. In essence, the spinning screws act as the primary energy source, while the grapplers act as the interface, transferring the energy to the sled by magnetically coupling with rotating screw threads. The variable pitch of the screws, combined with the controlled movement of the grapplers, allow for a smooth and constant acceleration of the launch sled. That's good. Why does the cost of other more traditional mass driver designs scale with the cube of the exit velocity? The sources provide a detailed explanation for the cube scaling of traditional mass driver designs. Rapid switching of electromagnets. Traditional mass drivers, such as coil guns and railguns, use electromagnets positioned along the length of the launch tube to accelerate a projectile. Okay, again, I think it's made this mistake of lumping railguns in with coil guns. So railguns do not use electromagnets positioned along the length of the launch tube, but coil guns do. So that's a mistake. As the projectile's velocity increases, these electromagnets need to switch on and off rapidly in a synchronized manner to create a moving magnetic field that propels the projectile forward. Yeah, this is correct. Power electronics and energy conversion. Rapid switching of high-powered electromagnets requires sophisticated and expensive power electronics. These electronics are responsible for storing electrical energy and delivering it to the electromagnets in short, intense pulses. The faster the projectile needs to go, the faster the switching time required for the electromagnets, and the greater the power demands placed on the power electronics. That's reasonable. That's accurate enough. Cubic relation with velocity. The cost of these high-powered, fast-switching power electronics scales approximately the cube of the exit velocity. I'm thinking this is a little bit unclear, but let's keep going. This means that if you want to double the exit velocity of a traditional mass driver, the cost of power electronics could increase by a factor of 8. Okay, well that's explaining what cubed means, but it isn't really answering the question of why it scales with a cube. It's just sort of restating that it is scaling with a cube. The source of this contrast is cubic scaling with the variable pitch screw launchers design, which aims to avoid this limitation. Mechanical energy transfer. VPSL uses spinning screws and magnetic grappers to transfer kinetic energy to the launch sled. This mechanical approach eliminates the need for rapidly switching electromagnets and the associated expensive power electronics. This is true. Velocity squared scaling. By relying on mechanical energy transfer, VPSL achieves a cost scaling that's proportional to the square of the exit velocity instead of v cubed. This makes VPSL a potentially more economically viable option for achieving the high velocities required for space launch. Again, this is another true statement, but I feel like this tool hasn't really successfully answered this question. And one of the sources that I uploaded did in fact talk about this. So let's see if we can find that source. Yeah, I think it's probably this one. So let's see if this is the right source. This is the right source, and I think it does go into the explanation. So if you read here, the variable pitch screw launcher cost scales with the exit velocity squared, which differentiates it from most other electromagnetic launchers. And then it tries to explain in this paper why that is. But I have a feeling that this AI has not really understood the math in this paper, and therefore it's having a hard time creating a kind of an explanation of it and passing it forward to us as a user. You can see kind of that the formulas are sort of all flattened. You would probably, if you were reading it this way, you would probably miss the essence of the explanation. So if we go to the original source, let me see if I can find it. This one here. So if you go to the original source, you can get a better understanding. The formulas are a little bit more clear, and the explanation starts, I think, roughly around here. So yeah, it says consider that a human-rated space launch will be quite long and thus must be comprised of many individual powered segments. If the vehicle travels past a segment faster, then the power electronics in that segment will have less time in which to add kinetic energy to the vehicle. So that segment must do more energy conversion in less time. Thus, it needs to be designed to handle more power. So this is kind of like the actual explanation, which is in the short 2-page paper. And it does some math, it does some integration to explain it all, sort of summarizes it, I think, at this point here. Then it talks about it's still better than rockets, which scale with the exponent of velocity. My feeling is that the tool is not able to understand this math and this explanation because it probably didn't really understand formulas that were in the paper. I probably wasn't able to parse them, and that's kind of why it. And this math and this explanation because it probably didn't really understand formulas that were in the paper. I probably wasn't able to parse them, and that's kind of why it ended up giving a weak answer on that question. So let's keep going. Yeah, so the next question is, what's this one down? Why hasn't this technology been implemented already? Here are several reasons why the variable pitch screw launcher technology hasn't been implemented yet, based on the provided sources. Novelty and perceived risk. VPSL is a relatively new and untested technology, especially when compared to the well-established field of chemical rockets. As discussed in the sources, investors, particularly government agencies accustomed to funding space exploration, often prioritize proven technologies with lower perceived risk. The sources highlight the need to build credibility and demonstrate the feasibility of VPSL through research, prototypes, and detailed engineering analysis to attract substantial funding required for its implementation. Long-term vision and funding horizon. Developing space infrastructure like VPSL requires a long-term vision and substantial upfront investment. The sources point out that traditional funding models, often driven by short-term gains and rapid returns on investment, might not be well suited for projects of this scale and complexity. Securing sustained funding over extended periods, likely through government initiatives or public-private partnerships, is crucial for realizing the long-term benefits of VPSL. Yeah, that's probably true. Technological challenges. While VPSL aims to overcome some limitations of traditional mass drivers, it still presents significant engineering challenges. Magnetic coupling and graphic control. The sources mention the need for further research and development related to the magnetic coupling mechanism between the grapplers and the screw plates. Ensuring efficient energy transfer and reliable operation at high speeds while accommodating the changing geometry of the screw threads requires precise control and robust engineering solutions. This is accurate again. Suspended evacuated tube. Extending the evacuated tube to high altitudes, as proposed in some VPL designs, poses considerable structural and engineering complexities. The sources discuss various options, including balloons, drones, and inertially supported structures, but acknowledge the need for further analysis and development to determine the most feasible and cost-effective approach. Scalability and reliability. Scaling up the VPSL design from small-scale prototypes to a full-fledged launch system capable of handling human-rated spacecraft presents significant engineering challenges. Ensuring the system's reliability, safety, and performance consistency at a much larger scale is crucial for gaining public and investor confidence. Public perception and institutional inertia. Gaining widespread public support and overcoming institutional inertia within the space industry are essential for the successful implementation of VPSL. The sources emphasize the importance of effectively communicating the potential benefits of VPSL and addressing concerns related to its feasibility, safety, and environmental impact. Shifting entrenched mindsets within government agencies, research institutions, and the public sphere towards embracing novel space infrastructure concepts is a gradual process that requires sustained effort and persuasive arguments. Well, I couldn't agree more. That's all very accurate. Okay, next question. What's going to happen when that vehicle traveling at well over supersonic, hypersonic speeds through an evacuated tube hits the air at the end of the tube? Yeah, this is the question, again, from the comments in the YouTube video. All right, the sources describe the vehicle exiting the evacuated tube of the VPSL system at hypersonic speeds, meaning speeds significantly faster than the speed of sound. While the tube protects the vehicle from aerodynamic forces during acceleration, it inevitably encounters air resistance upon exit. Here's a breakdown of what the sources say happens and how the system mitigates potential issues. Hypersonic flight regime. The vehicle exits the tube at an altitude of around 10 kilometers and a speed of roughly 11 kilometers per second. Sources acknowledge that this is a challenging flight regime, often associated with extreme temperatures and aerodynamic forces. Yeah, I think we plotted a variety of different altitudes and speeds of exit for the end of the evacuated tube, and not just the 10-kilometer altitude. I think some of the papers used 15 kilometers, and others used higher altitudes still, and other papers used lower altitudes and lower speeds. So there's been a variety of different speeds and altitudes mentioned in the papers, and I don't know why I picked 10 kilometers and roughly 11 kilometers per second. Next is rocket engine ignition. To counteract the sudden deceleration due to atmospheric drag, the vehicle fires a rocket engine as soon as it exits the tube. This kick burn helps maintain the vehicle's speed and ensures a smoother transition into the upper atmosphere. That is accurate. Aerodynamic design and thermal management. Sources emphasize the vehicle's streamlined design, featuring a long, narrow nose cone similar to NASA's X-59 or X-43A. The shape minimizes drag and reduces aerodynamic heating. Additionally, the vehicle utilizes transpiration cooling, circulating rocket propellant through the nose cone to prevent the tip from melting due to extreme temperatures. So this is partly accurate, except that's not really what transpiration cooling is. Transpiration cooling implies that the coolant kind of leaks out through a porous material in the nose cone, and it's a technology that I think creators of Startran were planning to use for their vehicles. It's not a bad idea, but it's not something that was proposed in any of the papers, and it's not same as circulating rocket propellants through the nose cone, which is just active cooling, but not transpiration cooling. So a little bit of a mistake there. Short atmospheric transit time. The vehicle only spends a short period, estimated to be about a minute, traveling through the atmosphere before reaching the vacuum of space. Okay, I would have said if I would have said about 20 seconds, not about a minute. Although technically, it might be a minute if you include the time it takes to actually get to the highest altitudes of perhaps 100 kilometers. But the time that you're actually traveling through a relatively thick atmosphere and experiencing a lot of aerodynamic heating is more like 20 seconds. This limited exposure helps minimize the overall thermal load and aerodynamic stress in the vehicle. Yeah, that's absolutely true. Because if you're not traveling in these flight regimes for a very long time, it's an easier engineering problem to solve than it would be if you had to travel through them for a long time. Potential for eyes out acceleration. The sources acknowledge that depending on the specific design parameters, passengers might experience a brief period of eyes out acceleration or deceleration when the vehicle transitions from the vacuum of the tube to the atmosphere. This deceleration, estimated up to 10 Gs for certain configurations, is comparable to what fighter pilots experience and its brief duration mitigates the risk of harm. So I think this was a bit misleading because we did a parametric study and studied many different altitudes and velocities for exiting the tube. And in the presentation, when I talked about that, I said that the worst case altitude and the worst case speed, which is the highest speed at the lowest altitude, you would see a 10 Gs of deceleration. But that was just sweeping a variety of different altitudes and speeds. It wasn't saying that that was the optimal speed and altitude. And in reality, though, most of the designs we propose have no deceleration because the rocket engine fires as soon as you leave the tube. So the idea is to have that synchronized so there's no deceleration at all. Or if there is going to be some deceleration, it'll be kind of like a jerk before the rocket engine kicks in. So this is a bit misleading to say that, that from the sweeping values in that parametric study, this is a relevant number to consider. The sources highlight that the combination of a high altitude exit point, short atmospheric transit time, a streamlined design, thermal management techniques, and a rocket engine boost allows the vehicle to safely and efficiently navigate the transition from the evacuated tube to the atmosphere. Yeah, that's pretty much accurate. It's important to note that the sources focus on technical feasibility of these mitigation strategies. They don't provide detailed analysis of passenger comfort or potential psychological effects during this high G hypersonic transition. I guess that's true, but there really is not meant to be any high G hypersonic transition. So that's kind of implying there is one. However, I believe, at one point mention that there's a possibility that the rocket engine would fail to fire. And in that event, there would be a significant amount of deceleration that the passengers would have to survive. So they would be surviving perhaps 10 Gs of deceleration if the rocket engine didn't fire. So it would be very desirable to have a reliable rocket engine. But if there wasn't a reliable rocket engine, quite likely that the passengers would survive, but they would not be on the right trajectory leaving the launcher. So that's probably an interesting topic to get into more later. All right, how much force do the arms that position the grapplers need to contend with? Let's break down the forces that the arms positioning the grapplers in a VPSL, variable pitch screw launcher, need to contend with. Sideways force from acceleration. As the launch sled accelerates down the tube, the grapplers attached to the sled experience a significant sideways force. This force is the direct result of the screw threads pulling the grapplers and consequently the sled forward. The sources provide a calculation for this force in the context of a specific design example. I'm not going to go over this whole design example, I think. Just keep moving forward. Next bullet is dynamic load management. The arms connecting the grapplers to the sled must be designed to handle this substantial and dynamic sideways force. They need to be strong enough to withstand the tension and prevent mechanical failure. The sources highlight the importance of engineering a lightweight yet robust chassis and arm system for the launch sled to accommodate these forces. This is all pretty accurate. Additional considerations. Beyond the primary sideways force, the arms also need to contend with vibrations and oscillations. The high-speed movement of the sled and rapid rotation of the screws can induce vibrations and oscillations in the system. The arms and their connections must be designed to dampen these vibrations and maintain stability of the grappler's magnetic coupling. This is not something that I ever said in any of the papers that were uploaded. I think this is kind of tool improvising a little bit. It doesn't really know if there's going to be vibrations and oscillations associated with these spinning screws, but it's reasonable to say that you need to engineer the screws so they're well balanced and they spin without vibrations and oscillations. So I guess it's a safe statement to make, but it's not something that was ever mentioned in the material I uploaded. It's kind of like a sort of generic engineering. This is a bit of a silly point, because insight, I suppose. Thermal expansion and contraction. The extreme temperatures generated during the launch can cause thermal expansion and contraction of materials. The arm's design must account for these thermal stresses and ensure grappler's precise positioning throughout the launch sequence. Oh, that's a bit extreme temperatures. So this is just complete made up bullshit, not accurate at all. Magnetic field interactions. The arms will be operating within a strong magnetic field generated by the screw's electromagnets. Okay, well the screws don't have electromagnets. There are motors inside the screws, but they don't emanate strong magnetic fields. Just like any other electric motor, the magnetic fields are contained tightly inside the casing of the motor, and outside the motor is very, very small magnetic fields, if any. So that's kind of not accurate, but there's some accuracy in the sense that the pads at the end of the grapplers will be strong magnets, and when they're interacting with the screw flights, those magnetic fields will be contained within the grappler pads and the screw flights. But again, they don't emanate so much from outside that the coupling. So the arms are not really operating within strong magnetic fields, but they do have to deal with the fact that the grapplers are attracting to the screw flights with a lot of force, and so there's a sort of mechanical stress associated with that. The materials and design of the harness must minimize any interference or unwanted interactions with these magnetic fields. So this is all not accurate at all. This is kind of made up stuff that's kind of shows that the tool does not really understand the technology. Um, so this is interesting. It's kind of something like you might say if you were sort of like a hack at engineering and you heard that the technology was magnetic fields, then you might say, oh, there's some other technology out there that has to deal with strong magnetic fields, like maybe like a fusion experiment or something. But it doesn't show that this particular tool understands the technology at that level. And let's keep going. The sources don't provide specific force calculations for these additional considerations, but they emphasize the need for a comprehensive engineering analysis to ensure the arm's reliability and performance under the demanding conditions of a VPSL launch. Okay, that's fine. All right, so that whole answer was a little bit iffy, I would say. It kind of embellished and didn't do a good job on some of those embellishments. All right, the next one. If the elevated tube is held up by drones, how long can they stay aloft before they run out of power? This again was a question that I think came up in the comments of the YouTube video. The sources don't provide specific details about using drones to support the elevated tube, of the VPSL system or their potential flight times. However, they do offer some relevant insights. Source 1 mentions using drones as a potential short-term solution for supporting the evacuated tube. This suggests that the idea of drone-based support has been considered within the broader context of VPSL design. However, the source also highlights potential drawbacks, such as winds. Strong winds at high altitudes could pose challenges for maintaining the stability and positioning of drones, and maintenance. The need for regular maintenance of a large fleet of drones operating at high altitudes could introduce logistical complexities and costs. That's all very reasonable. Source 1 suggests that inertially supported structures, similar to the concept behind an orbital ring, might be a more suitable long-term solution for supporting the tube. I would have said the concept behind a tethered ring there, but I guess more people know what an orbital ring is than a tethered ring. Source 2 discusses using drones to shepherd cable phase in the context of a different space infrastructure concept, a space fountain. I don't think that is true. I wonder what source 2 is in this case. It's interesting, we can actually click on the source and have a look at it and see how it came to that conclusion. This is a very original paper on the tethered ring that I wrote back in 2015. And at the time, I was talking about using drones to shepherd the stays of the tethered ring, not shepherd the stays of a space fountain. So I don't know where the space fountain came from. That's kind of interesting that it sort of added that in there, but I'm pretty sure I never talked about a space fountain in any of these articles or any of these papers that I uploaded. So I don't know where it got that from, but it definitely invented that. While not directly comparable to supporting a VPSL tube, this example illustrates the potential for using drones to stabilize and guide large structures at high altitudes. Okay. All right, next is none of the sources provide information on power sources or flight times of drones that might be used in a VPSL context. To estimate drone flight times, you would need additional information such as drone type and size, payload capacity, battery technology, altitude and wind conditions. Therefore, while the sources suggest that using drones to support a VPSL tube is a concept worth exploring, they don't provide the necessary details to determine how long such drones could stay aloft. Further research and analysis, considering the factors mentioned above, would be needed to assess the feasibility of this approach. Okay, in this case, I feel like this tool had kind of failed here because I think it's pretty obvious that if you're using drones to support a structure that's connected to the ground, which is what the elevated evacuated tube is, that it would be pretty obvious that you could bring the power up the tube on using electrical cables to power the drones. So that your power supply could be a power plant located on the ground, and you just use high voltage cables to bring the power to the drones. And so you wouldn't even need batteries in the drones at all. So that is the intent of the design. And although I don't think it was mentioned in any of the material I uploaded, I think your average engineer, considering this problem, would have been able to make that deduction. And this tool failed to make that deduction. So I don't think this is demonstrating that it's as smart as your average engineer. Also, I feel pretty confident that at least some of the papers that I wrote where where drones were used or aeronautic support was used to shepherd the stays or kind of for station keeping purposes, that in that use case, I mentioned that the power would be coming from the stays themselves. In other words, there wouldn't be batteries in these drones or aeronautic support devices. So I feel like this has been covered in other material. I can't remember exactly what material covered that, but I'm pretty sure that that was covered. So this answer was not particularly good because it completely missed the idea of supplying the drones power from the ground. All right, let's go to the next one. What is the energy efficiency of the VPSL system? Well, here's what the sources say about the energy efficiency of the VPSL system. The VPSL aims for a high electrical to kinetic energy conversion efficiency. Sources highlight that the VPSL system is designed to efficiently convert electrical energy into kinetic energy of the launched spacecraft. One source states that a reasonable assumption for this conversion efficiency, represented as E or epsilon, is 50% for interplanetary missions. However, the source acknowledges that future research on efficiency of electrical to kinetic energy transfer in high-speed linear motors would improve the accuracy of economic analysis related to the VPSL. Hmm. I don't know if I would have ever said that, that the linear motor's efficiency was relevant to the VPSL efficiency, because the VPSL is not the typical linear motor. It's really just a regular rotational motor on the inside spinning the screws, and then effectively it's a magnetic worm gear, which is not a linear motor. So I think this might be a little bit made up, but I'm not 100% sure about that. What's the reference in this case? Reference for colonization by using a tethered ring. Okay, this is an earlier paper on economics. So I haven't read that paper in a long time, so I better go back and check that again. But I feel like it's probably wrong. This answer is probably slightly wrong. Energy consumption per launch. Another source provides a more optimistic view of the system's efficiency, stating that the energy consumed per launch can be calculated using the following formula, which takes into account regenerative deceleration of the launch sled. Yeah, this is good. This is more updated and more recent. Using the formula with specific design parameters and a bunch of formatting. It's hard to read. Both equal to 28 tons, epsilon at 0.9, V at 11,120 meters per second, and a payload fraction of 0.613. The source calculates the energy consumption of 2.8 terajoules, which translates to 0.134 gigajoules per kilogram of payload, or $1.85 US dollars per kilogram of payload sent to Mars. Again, this is the $1.85 is the cost of the power that's being fed into the system. According to this calculation, it's not the cost per kilogram of the entire, like, it's not the fully considered cost per kilogram of the system, which it doesn't include the amortization of capital costs. And that's a bit misleading, but we are talking about power in this answer, so and energy efficiency, so I think that's not too bad. Factors affecting efficiency. While the sources don't provide a single definitive value for the VPSL system's overall energy efficiency, they highlight several factors that contribute to its efficiency. Regenerative deceleration of the sled. The launch sled's ability to decelerate regeneratively, as mentioned in the previous point, recovers some of the energy expended during the launch and reduces the overall energy consumption. This is accurate. Minimized air friction. The evacuated launch tube significantly reduces air resistance, minimizing energy losses due to drag. Correct. Efficient electric motors. The system uses electric motors to spin the screws, and these motors are generally very efficient at converting electrical energy into kinetic energy. Actually, very true again. It can be like 95% efficient in some cases. Earth as reaction mass. By using the Earth as the reaction mass, the system avoids the need to carry propellant for acceleration, further improving its overall efficiency. Very good. These are all excellent points. And I think I've pretty much covered them all as well. Comparison to traditional rockets. The sources consistently emphasize that the VPSL system offers a significant advantage over traditional rockets regarding energy efficiency. Traditional rockets rely on chemical propulsion, which is inherently less efficient than electrical to kinetic energy conversion, particularly for missions beyond low Earth orbit. In summary, while the sources provide some insights into the VPSL system's energy efficiency, they don't offer a definitive, all-encompassing value. The system's efficiency would depend on various factors, including specific design parameters, operating conditions, and the mission profile. However, the sources consistently highlight that VPSL's system design, which minimizes energy losses and maximizes energy recovery, position it as a significantly more energy efficient alternative to traditional chemical rockets, especially for missions to destinations like Mars. All right, that was a long answer, but it wasn't too bad. Going back over that, I thought this part was pretty good about capturing all the different factors. And other than sort of misleading people a bit with this 1.85 US dollar figure, it was still pretty good. Yeah, I think it was not too bad. Okay, next, can you create a fact for the VPSL technology? Well, it chewed on that and then said the system was unable to answer. So I guess this was too complicated for creating a FAQ. What are the top technical and economic challenges for the BPSL system? Okay, here are the top technical and economic challenges for the BPSL system based on the provided sources and our conversation history. Interesting, it's mentioning conversation history now, because we haven't really had a conversation. We've just been asking questions. So maybe it's saying, it's going to refer back to things it said in the past. Top technical challenges: grappler design and magnetic coupling. The sources mentioned that the grapplers, which magnetically couple to the launch sled, to the screw threads, are a critical and complex component of the BPSL system. Designing grapplers that can withstand the immense sideways forces, vibrations, and thermal stresses during launch while maintaining a stable magnetic coupling is a significant technical hurdle. The sources in our conversation don't go into great detail about how the grapplers are designed or how the magnetic coupling mechanism works. This suggests that these are areas requiring further research and development. I feel like there's a paper that goes into a fair bit of detail on how the magnetic coupling system works, so I don't think that's completely accurate. Um, it's possible that again it didn't really understand the paper's explanation of that, and it couldn't see the figures. It didn't really have the ability to actually visually interpret the figures, which I think an engineer would have interpreted. And so without looking at the figures and the equations and then in the context of the text, you may not come away with an understanding of how the coupling mechanism works. So that this does imply that the tool is just reading the text and maybe not looking or understanding the figures that it's been given. Additionally, the sources mention the need to study the challenges of repositioning the magnetic pads as the sled surfs the screw plates. Okay. Thermal management. The high speeds involved in the BPSL launch system generate extreme temperatures, particularly at the vehicle's nose cone as it transitions from the evacuated tube into the atmosphere. Yes, this is true. The sources mention using transpiration cooling, circulating rocket propellants through the nose cone to mitigate this heat. I must have mentioned transpiration cooling somewhere, so it's mentioned it twice, so I'll have to go back and look for that. However, they acknowledge that more engineering work is needed on the cost and feasibility of the thermal protection system. Yeah, I think that's fair. It's an area where there's not a lot of data because most of the work that's been done in hypersonics or related to ICBM reentry vehicles is kind of secret information that's not widely published. So it's hard to get your hands on that kind of information. Managing the heat generated by the rapidly spinning screws and other components within the evacuated tube is also crucial. Interesting. I don't know if I ever mentioned that, thermal management of the heat generated by the rapidly spinning screws in any of the papers. It might have just inferred that this is something that needs to be considered because obviously, if the motors are inside the screws and the screws are inside a vacuum, they're fairly well insulated. So the only way the heat is going to get out is through either conduction through the brackets or through radiation into the environment or through some sort of active cooling. And in fact, that's what we think is necessary. We'll need to do. We think we'll need to pump coolant into the screws to cool the motors down. So, but that was never mentioned in any of these papers, to the best of my knowledge. Suspended evacuated tube. The VPSL concept relies on a long, elevated evacuated tube to guide the vehicle to a sufficient altitude before it exits into the atmosphere. Constructing and maintaining such a large and elevated structure presents significant engineering challenges. The sources propose several options, including building on a high altitude plateau, supporting the tube with balloons or drones, using inertially supported structures similar to the concept of an orbital ring. Each option has its own set of technical hurdles, and the sources don't definitively endorse a single solution. I think that's true. I think lately I've been looking into using drone technology to support it, and I don't believe in balloons. And I have in the past talked about using a tethered ring to support it. And in the presentation that I gave earlier this year, at the International Space Development Conference. That was about the idea of using a smaller inertially supported structure called the space fountain to support the tube. So there's been a lot of ideas kicked around, and it's true there's definitely no kind of definitive solution that we've endorsed. Okay, top economic challenges. High capital costs. The sources acknowledge that building a VPSL system would require substantial upfront investment. While the sources emphasize that the VPSL's operating costs per launch would be significantly lower than those of traditional rockets, securing the initial funding for a large-scale infrastructure project proposes a significant economic challenge. The estimated capital cost for a full-scale VPSL system, the estimated capital costs for a full-scale VPSL system vary across the sources. For instance, one source estimates the capital cost of $32 billion for a system capable of launching spacecraft to Mars transfer orbit. Another source estimates the capital cost of $7 billion. Okay, this other source, $7 billion, was an earlier estimate that was saying that it estimated the materials cost at $7 billion. It wasn't the total cost. So it's kind of mixing up the materials cost estimate here and calling it a capital cost estimate and then saying it's different. So it just didn't understand that this was a materials cost estimate, not a total capital cost estimate. So anyway, let's keep going. Okay, for VPSL mass driver capable of delivering 21,566 metric tons of payload to Mars over 10 launch windows. This discrepancy highlights the need for more detailed economic analysis to refine the cost estimates and identify potential cost-saving measures. Well, it's certainly true that we do need more detailed economic analysis and need to refine the estimates. But the discrepancy was really in the tool's failure to understand that the $7 billion was for a different thing. Improving technology and investor confidence. The VPSL, while promising, remains a largely untested technology. Investors might be hesitant to commit significant funds to a project with no proven track record. That's fair enough. Demonstrating the technical feasibility of VPSL through smaller scale prototypes and rigorous simulations would be crucial for building investor confidence and attracting funding. Competition from existing launch providers. The commercial space launch market is becoming increasingly competitive, with established players like SpaceX driving down launch costs through reusable rocket technology. The VPSL would need to demonstrate a compelling economic advantage over these existing providers, either through significantly lower launch costs or the ability to service niche markets that traditional rockets cannot. The sources highlight the importance of considering the total cost of a mission, including factors such as environmental impact and the ability to support round trips and crewed missions when comparing the VPSL to rocket-based systems. I think in some of the material I uploaded, there were arguments to say that SpaceX is not driving down launch costs as much as a lot of people think they are. At least didn't say that there was any amazing amount of cost reduction through reusable rocket technology. So I haven't really passed on any misinformation there. It just says that they're driving down costs through reusable rocket technology. But the sources that I uploaded argued that the amount of reduction in launch costs is not that significant. It may be a factor of 2, not like a factor of 10 or anything. Okay, so let's continue. Summary. The VPSL system presents both exciting opportunities and significant challenges. Addressing the technical hurdles related to graphic design, thermal management, and the suspended evacuated tube will be essential for proving the system's feasibility. Overcoming the economic challenges of high capital costs, building investor confidence, and competing with established launch providers will be crucial for making the VPSL a commercial reality. All right, I think I'm going to skip this one. It's been a long analysis so far, but I did think it came up with some pretty good suggestions for titles. I asked it to suggest some titles, and I think they're pretty good titles. And it gives some rationale and advice on that whole selecting a title question. To explain the advantages of using a variable pitch screw launcher compared to traditional mass driver designs. The advantages of a variable pitch screw launcher over traditional mass drivers. The sources consistently highlight the key advantages of the VPSL system over traditional mass drivers. Improved cost scaling with velocity. This advantage stems from the VPSL's unique mechanism for accelerating a payload, which avoids the need for rapidly switching electromagnets, a characteristic of many traditional mass driver designs like coil guns. And again, I put railguns in with coil guns. I don't know why it's doing that. Here's a breakdown of the key advantages, drawing on the sources and our conversation history. Velocity squared scaling. The sources emphasize that VPSL systems cost scales with the square of the exit velocity, a significant improvement over traditional mass drivers where a significant portion of the cost scales with the cube of the exit velocity. Okay, this is accurate. This difference in scaling arises from how each system imparts kinetic energy to the payload. Traditional mass drivers typically rely on a series of electromagnets that rapidly switch on and off to generate a moving magnetic field that propels the payload. As the desired velocity increases, these electromagnets need to switch faster and handle more power, leading to a V cube scaling for the expense of power electronics components. This is good. It's actually got this right. In contrast, the VPSL system first gradually stores kinetic energy in its rotating screws. The stored energy is then rapidly transferred to the payload more mechanically through the magnetic coupling between the screw threads and the launch sled. By avoiding the need for rapidly switching high-powered electromagnets along the length of the launcher, the VPSL system achieves a more favorable V-squared cost scaling. Yeah, that's very well described. It's a good summary of how that works. Eliminating pulsed power electronics. The sources point out that the VPSL system's reliance on rotating machinery and magnetic coupling eliminates the need for the distributed high power pulse power electronics required by many traditional mass driver designs. I think in this case it would be fair to lump in railguns. For long railguns do need distributed high power pulse power electronics. These pulse power systems, essential for rapidly switching electromagnets on and off in traditional mass drivers, are complex, expensive, and can be a significant contributor to the overall system cost. And this is definitely true. If you read the Wikipedia article on StarTram, for example, this is one of the top concerns that is mentioned in the concerns section of that article. By circumventing the need for such systems, the VPSL architecture achieves a cost advantage, particularly as the desired launch velocity increases. Mechanical wave analogy. The sources use the analogy of surfing a mechanical wave to describe how the VPSL system accelerates the launch sled. This analogy highlights how the rotating screws, powered by electric motors, create a moving magnetic field that the sled grapplers can ride to gain velocity. Okay, I don't know if I would say that the rotating screws create a moving magnetic field exactly. I think it's really just a mechanical wave here. There's not a moving magnetic field per se. There is magnetism used to attract the grappler's magnetic pads to the screw flights, but if you just looked at the screws on their own without the vehicle traveling, there wouldn't be a moving magnetic field. There's just a spinning screw, a mechanical spinning screw. So this I feel is a bit inaccurate. This mechanical wave-like acceleration, enabled by the variable pitch of the screws, allows for a more gradual and controlled energy transfer to the payload, potentially leading to lower peak power demands and reduced stress on the system's components compared to the more abrupt acceleration profiles of some traditional mass driver designs. Yeah, so I think that's a fair point. A lot of mass driver designs people are familiar with have extremely high accelerations, such as rail guns, for example, and even some of the prototype designs that Gerard O'Neill and some of the people that worked with him came up with had extremely high and very abrupt acceleration profiles as well. So yeah, historically these mass drivers have had like a very fast and jerky acceleration that would do a lot of damage to many kinds of payloads, like such as humans. And the VPSL technology is definitely a more gradual and controlled acceleration. Okay, next, reduced rail wear. While not explicitly discussed in the context of comparing cost scaling, the sources mention that the VPSL design eliminates the rail wear commonly associated with rail guns. Absolutely true. Railware in railguns is a major issue. There was a lot of research at the recent electromagnetic launch conference that took place in Amsterdam this year. It seems to be an area of ongoing research. This advantage, while potentially less significant in terms of overall cost compared to the v-squared scaling, further contributes to the VPSL system's potential for lowering operating and maintenance costs over traditional railgun-based mass drivers. Actually, this is a significant advantage because in a railgun-based mass driver, if you have to do a lot of maintenance in the rails, it makes the cost extremely expensive. So the fact that there is no wear, like no pitting or erosion of the parts of the VPSL launcher as it's used to launch and accelerate payloads, is really very important for cost. If somebody tried to do the same thing with a railgun, it might actually require less in terms of materials to construct the technology, just the rails, not the power electronics, but just the rails themselves might be cheaper to construct. But if those rails were worn out after a few launches because of the large amounts of current traveling between the armature and the rails, creating a lot of pitting and erosion, electromagnetic erosion from the plasmas that are being managed in those electricity transfers. Yeah, you'd basically have a device that was useless after a few launches and would have to be replaced or extensively refurbished. So reducing railway relative to railguns is a very important economic point. In summary, the VPSL system's unique approach to electromagnetic launch, utilizing rotating variable pitch screws and magnetic coupling, offers several advantages over traditional mass driver designs, particularly in terms of cost scaling, especially for high velocity launch applications. This approach could pave the way for more economically viable space launch infrastructure, enabling more ambitious and frequent missions beyond Earth orbit. Very well said. All right. Boy, this is taking a while to get through. What are the main benefits of using a variable pitch screw launch system for a human-rated spacecraft? The sources, particularly the technical papers focused on the variable pitch screw launch system, highlight numerous benefits for the application in launching human-rated spacecraft. The sources, particularly the technical papers focusing on the variable pitch screw launch system, highlight numerous benefits for its application in launching human-rated spacecraft. These benefits span economic advantages, enhanced safety considerations for human passengers, and environmental sustainability. Oh, this is a long answer. I don't know if I want to read all this. Let's see if there's any interesting points. I'm just going to skim over this. We talked about reduced costs. We talked shifting from expendable to reusable. Hmm. So it is sort of true that we're shifting from expendable to reusable if you consider expendable rockets, but this implies that that there are reusable rockets, obviously, like the Space Shuttle, Falcon 9, Falcon Heavy, all have reusable components. In fact, they're arguably 98% reusable. I think perhaps the Falcon 9 is one of the most reusable because it reuses its core stage, its fairings, and it reuses all the launch infrastructure like the gantries and the towers. It reuses the ships, the autonomous drone ships that the boosters land on. It reuses the Dragon capsule. The only thing it doesn't reuse is the second stage and the engine on the second stage. And I think the trunk, if it's a trip to the space station, it doesn't reuse the trunk. So that's pretty good. The space shuttle reused everything except for the main tank, which is a fairly big component, but it wasn't a very expensive component as I understand it. And Falcon Heavy reuses the two side boosters and the fairings, but I don't think it ever reuses the core stage or the second stage, so it's not quite as reusable as the Falcon 9. But nevertheless, the reusability of a system when you're going to Mars is kind of limited because you can't really get the ships back from Mars very easily. It takes a long time. Like they're going to be gone for years. So when you send things to Mars, sort of by definition, there's non-reusable components that are going to Mars. I mean, if they were reused, they would be reused after 5 years, perhaps, and they'd probably be obsolete by the time they got back. So you just can't really get great reusability when you're going to Mars. So I don't know, shifting from expendable to reusable, I don't know if this is a strong point. I feel like it's a point that's more related to I think a lot of ideas have been promoted in the rocket space of going from expendable to reusable, but it's not really a strong point for infrastructure. Even though infrastructure is very reusable, I don't feel it's a strong point. Okay, focus on energy, not propellant. Unlike chemical rockets, which require vast amounts of propellant to reach high velocities, the VPSL system primarily relies on electricity, a more sustainable and potentially cheaper energy source. This fundamental difference in energy consumption contributes significantly to the VPSL system's projected cost advantage, particularly for missions requiring high delta V, such as those to Mars. Okay, safety considerations for human passengers, a smoother ride to space. Controlled acceleration. The sources highlight the VPSL system's ability to provide a smoother, more controlled acceleration profile compared to the intense, short duration thrust of chemical rockets. I don't know. Let me have a look at the source and see where it said that. Yeah, it's highlighting some text here, but it doesn't say that in the highlighted text. Let's try this one. It's just a bunch of formulas. And this one? Yeah, I don't feel like this point is well supported. And the VPL system does provide a smooth acceleration profile, but it's actually probably more intense than a chemical rocket. A chemical rocket's acceleration profile is typically about 3 Gs, and it might be a bit of a shakier ride, but it's not quite as intense as a launch from mass driver. So the mass driver designs we propose do have higher accelerations than rockets, even if they're fairly smooth. So I don't think this is a very good point. The acceleration is controlled, but it's not. It is more intense than that you would see in a chemical rocket. So this next part is definitely not true. This gentle acceleration spread out over longer distance could be crucial for ensuring the safety and comfort of human passengers, potentially reducing the risk of injury from high G forces. So this is completely wrong. Everything that we've uploaded, I uploaded to the tool, talked about higher accelerations than we typically see in rockets. And this is just, of course, to reduce the length of the mass driver to reduce its cost. Theoretically, I guess you could make a ridiculously long mass driver that would have lower G forces, but everything we proposed is higher G forces, and use advanced acceleration couches to ensure the comfort of human passengers, not lowering G forces. All right, reduced atmospheric drag. The sources discuss launching spacecraft from high altitudes to minimize atmospheric drag and the associated heating effects. The VPSL system, with its ability to launch spacecraft from elevated positions, either through extended evacuated tubes supported by various methods, or by taking advantage of high altitude terrain, could reduce the need for robust and heavy thermal protection systems on the spacecraft itself. This in turn improves the overall mass efficiency and potentially allows for larger payloads or more comfortable crew accommodations. To go back to this question, for the benefits here, I don't know if you asked your average engineer what the benefits of this technology were, if they would say that it reduces atmospheric drag. I think quite the opposite would be the typical response. They would say something along the lines of one of the technology's most obvious challenges is dealing with the large amount of atmospheric drag. I guess relative to other designs proposals, perhaps this reduced atmospheric drag. For example, if somebody had proposed like the Star Tram version or Generation 1 launcher, which just launched on the top of the mountain, that would have had a lot of atmospheric drag initially because it's still fairly deep in the atmosphere. And this launcher proposes to go through an evacuated tube and exit higher into the atmosphere, kind of like Star Tram version 2 or Generation 2. Yeah, I just don't feel like reduced atmospheric drag is an advantage or a main benefit for human rated spacecraft. I think it's kind of a misunderstanding of the technology there. All right, next one is redundancy and system reliability. While the sources don't explicitly detail redundancy measures within the VPSL system, its reliance on proven technologies like electric motors, flywheels, and magnetic levitation systems suggests a potential for high reliability through component redundancy and well-established maintenance practices. This would be crucial for ensuring the safety of human passengers. I guess that's a fair point. There's a lot of components in the system that are we have a lot of experience with. Like electric motors are fairly reliable these days. Magnetic levitation systems are also used in several trains today, and they seem to be working just fine. So I think I have to agree with that point. Environmental sustainability, launching a greener future. Renewable energy source. The sources emphasize the VPSL system's compatibility with renewable energy sources. As a primarily electrically driven system, it can leverage clean energy from sources like solar, wind, or hydroelectric power, significantly reducing the environmental impact associated with the traditional rocket launches that rely on fossil fuels. Absolutely accurate. Minimal atmospheric pollution. By launching spacecraft from evacuated tubes, the VPSL system minimizes the release of pollutants and greenhouse gases into the atmosphere. This is in stark contrast to chemical rockets, which release significant amounts of exhaust products, potentially contributing to air pollution and climate change. Yep, that's definitely true. And reduced noise pollution. The sources mention the potential for reduced noise pollution with the VPSL system, particularly when using evacuated launch tubes that extend to high altitudes. This benefit, while perhaps less critical than reducing greenhouse gas emissions, could be significant for communities located near launch sites. Yeah, I think this is a pretty significant point. When you consider the amount of land area around a rocket launch site, when you're launching a very large and expensive, I shouldn't say expensive, a very large and loud rocket like Starship, there's a lot of land area that is disturbed by the noise of the launch. And that can be exciting during development when you're launching a rocket, 2 or 3 times a year and tourists want to go down and see it. That's great. But when you get into the regime of wanting to launch a rocket every day, then you're basically going to have to somehow compensate all the people who live within, I don't know, 10, 20 miles of your launch site to get them to be okay with that. They'll either sue you to prevent you from launching, or they'll force you to go somewhere else, like to a desert where there's no people living, or offshore where there's a lot more technical challenges associated with doing a launch from some sort of offshore platform. So the noise pollution is a significant factor in terms of the costs and economic viability of the system. And so when you consider when we're scaling up to the launch rates that we would need to go to Mars or support a supply line to Mars, then this becomes a significant factor. Conclusion, a transformative step towards sustainable space exploration. In contrast, the VPSL system presents a compelling vision for the future of human spaceflight, offering a unique combination of economic viability, enhanced safety, and environmental sustainability. By addressing some of the fundamental limitations of traditional chemical rockets, the VPSL system has the potential to revolutionize our approach to space exploration, making it more affordable, accessible, and environmentally responsible. As humanity sets its sights on ambitious goals like establishing a sustained presence on Mars, the VPSL system represents a promising path towards achieving these aspirations. Well, that's a well-written kind of concluding statement. So I think that was pretty good. All right, let's see if we can go to the next question. Put that one down. What are the main challenges associated with the use of railguns and coil guns for launching payloads into space? I think we've sort of been over this before. I don't want to have to rehash that one. Yeah, we've talked about this. I think it's done a pretty good job of summarizing these main challenges. So interesting, but let's not rehash that point. What are the advantages of a tethered ring launch system over other non-rocket launch technologies such as spacebound and launch boosts? I don't know if this was relevant to the topic we're talking about, so I might read that later, but I feel like this is something that I might have accidentally clicked on a question that it proposed to me, and I probably wouldn't have asked that question. All right, last one. If your goal is to debunk VPSL technology, what points would you make? Debunking VPSL technology, identifying potential weaknesses. While the sources present a generally optimistic view of VPSL technology, a critical analysis reveals potential weaknesses and challenges that could hinder its practical implementation and effectiveness as a viable alternative to chemical rockets for space launch. 1. Scaling challenges and engineering complexity, from prototype to full-scale implementation. Unproven scalability. While the sources provide simulations and calculations suggesting VPSL's feasibility, the technology remains largely untested at a scale necessary for space launch. The jump from small-scale prototypes, like the one mentioned in 1, to a full-scale system capable of accelerating payloads to 11,129 meters per second, 2, represents formidable engineering hurdles. Issues related to material strength, structural integrity, thermal management, and maintaining precise alignment over a 773-kilometer distance could become exponentially more challenging with increasing scale. Complexity of the adaptive net. The sources mention the adaptive net, Figure 3 and Source 4, not included in the provided excerpts, as a key component for maintaining magnetic coupling between the launch sled and the variable pitch screws. The precise and rapid adjustments required for the adaptive net to function effectively over the entire length of the launch tube would necessitate sophisticated control systems and likely involve a large number of moving parts. The complexity could increase the risk of failures, drive up manufacturing and maintenance costs, and potentially impact overall reliability. Yeah, okay, it's fair. Magnetic shielding and eddy currents. Even with the absence of rapidly switching electromagnets, the presence of strong magnetic field in the VPSL system could still induce eddy currents in nearby conductive materials, leading to energy losses and potential heating issues. Effective magnetic shielding would be crucial to mitigate these effects. But designing, implementing, and maintaining such shielding over a large-scale VPSL system could add significant complexity and cost. Yeah, that is a very good point. Economic viability and uncertain cost projections, the need for rigorous analysis. Overly optimistic cost estimates. The sources, particularly 3, provide a relatively low estimated capital cost of 32.6 billion US dollars for a full-scale VPSL system. However, this estimate relies heavily on assumptions about material costs, manufacturing processes, and the ability to repurpose existing infrastructure, which may not reflect real-world conditions. Sources also acknowledge potential additional costs, such as power grid upgrades, which could further inflate the overall project budget. Lack of independent verification. The cost projections presented in the sources appear to stem primarily from the creators of the VPSL concept and their digital twin model. Independent verification of these cost estimates by external experts would be crucial to establish their credibility and assess the true economic viability of the VPSL technology. I agree with that too. Long-term operational costs. The sources focus primarily on capital costs, but the long-term operational costs of the VPSL system, including maintenance, repairs, energy consumption, and personnel, could be substantial. A comprehensive analysis, considering both capital and operational costs over the system's lifespan, is essential for a realistic assessment of its economic feasibility. Yeah, that's fair. Technical feasibility and unresolved challenges, addressing potential bottlenecks. Evacuated tube design and construction. The VPSL concept relies heavily on maintaining a near perfect vacuum within a 773-kilometer long tube. Constructing and maintaining such a long, evacuated tube would present unprecedented engineering challenges, especially considering factors like thermal expansion and contraction, material fatigue, seismic activity, and the need for regular inspection and maintenance. I don't know if I agree with this one so much, but I think there's probably a lot of people out there who would agree with this, so we'll leave it. But I think we have a fair bit of experience designing evacuated tubes and constructing things like spiral welded steel tubes. All right, launch vehicle separation and aerodynamic heating. As the launch vehicle exits the evacuated tube at hypersonic speeds, it will encounter intense aerodynamic heating and shock waves. The sources briefly mention a streamlined vehicle design and the potential use of a plasma window technology, but they do not provide sufficient detail on how these measures would effectively address the challenges of hypersonic flight and ensure the vehicle's structural integrity and payload safety. So I don't know, I think I might have mentioned plasma windows at one point. This is really an idea that came from the StarTram technology. I think it might be legit. but I don't really propose that we need to use it for the VPSL. I think the VPSL will be better served by punching through a membrane at the end of the launcher and then having a fast door closed behind the vehicle to keep the air from rushing in. But it is fair to say that aerodynamic heating of the vehicle is going to be one of the places where design trades have to be made between making the height at the end of the evacuated tube higher in the atmosphere to reduce the aerodynamic heating versus designing the vehicles to be able to tolerate more aerodynamic heating. So there's a trade there, which is an area where further research definitely needs to be done. Energy storage and transfer efficiency. The sources mention flywheels as a potential energy storage mechanism, but they do not provide detailed information about the efficiency of energy transfer between the flywheels, screw segments, and launch sled. Energy losses during these transfers could reduce the overall efficiency of the VBSL system and necessitate more powerful and expensive power infrastructure. I suppose, yeah. We haven't talked a lot about flywheels in papers because it's getting into proprietary areas, and so it's not this material isn't published. This is an area where we have done some work, but we haven't really published it. Okay, environmental considerations and the potential risks beyond carbon footprint. Noise pollution from supersonic flight. Even with an extended evacuated tube, the launch vehicle will eventually transition into supersonic flight in the upper atmosphere, generating sonic booms that could have significant noise pollution impacts on surrounding areas. The sources acknowledge the need to mitigate noise pollution, but they do not provide concrete solutions for addressing this challenge, which could face public opposition and regulatory hurdles. That's a fair point. I'm not going to go into that now, but I do think it's something that can be addressed. The noise pollution that will be caused by the supersonic booms in at least one of the architectures at one of the sites that we've considered would be over the ocean. So hopefully not a problem. But it's still an area where there hasn't been anything really published to talk about that. Ecosystem disruption during construction. Building a large-scale VPSL system, especially the mountainside ramp and potentially sea-based launch tube, could have significant environmental impacts during the construction phase. I don't know about that. Tunneling a ramp and putting a pipeline in the ocean, they're not significant environmental impacts. They have some environmental impact, but this is something that we do fairly routinely. So I don't think it's fair to call it a significant environmental impact, especially as we would be reducing the number of polluting launches by a significant amount if we built this technology. Habitat disruption, noise pollution from construction activities, and potential waste disposal issues would require careful assessment and mitigation strategies. Limited launch site flexibility. The VPSL concept requires a specific geographic location with a suitable mountainside for the launch ramp and potentially access to a large body of water for a submerged launch tube. The limited launch site flexibility could restrict mission parameters and potentially increase costs associated with transporting payloads and personnel to remote locations. Yeah, I suppose, but it's a lot cheaper than rockets, so I don't think that will be a big deal. Conclusion, call for a critical evaluation and further research. While the VPSL concept presents an intriguing approach to space launch, a balanced assessment reveals potential weaknesses that warrant careful scrutiny. Addressing the scaling challenges, verifying the economic projections, providing detailed solutions for technical hurdles, and thoroughly evaluating environmental impacts are crucial steps towards determining the true viability of VPSL technology. Further research and development are essential before it can be considered a realistic alternative to conventional rocket-based launch systems. Yeah, that's a pretty good answer. I agree with the summary, and there definitely is more work to be done. So overall, my feeling about this tool, which is NotebookLM from Google, is that yeah, it's like ChatGPT. When ChatGPT came out, it was very impressive in its ability to appear intelligent. I think it has done a very good job at summarizing material that was in the papers, and it's very eloquent. It's able to say things very clearly, and in some cases, I think it made statements in ways that are better than some of the statements that were in the original papers. So it sort of summarized them very effectively. When it was called upon to understand something that was in a figure or captured in mathematical form in the papers, I feel like it was a little bit weaker. It maybe didn't understand formulas that were in papers or didn't understand figures in papers the way a human would have understood those things. It relied mostly on the text descriptions to gain its knowledge or build its knowledge. So that's a potential weakness. And I feel that occasionally it relied on what I would call general knowledge to make points. So it wasn't entirely focusing on what the paper said. It would bring in general knowledge and try to apply it like an engineer typically would to what it was seeing, and not necessarily doing that mapping very well. So when we asked it about earlier on about what was it now? Yeah, it was this question about the passenger who need to wait in the vehicle. It came up with a kind of a bit of a bizarre answer that showed that it didn't have a real understanding of technology the way a human engineer would have understood it. And and similarly, when it was asked about the drones and how the drones and how long the drones would last, it didn't have the ability to kind of deduce that the drones could be powered from the ground. So obviously, it would be better if I wrote papers that made that clear. And I haven't really talked a lot about the types of support mechanisms used for the elevated tube in most of the papers so far. But I think a human engineer would have done better on those kinds of questions. It would have figured out that that was a possible solution. In fact, a human engineer might even propose other solutions that might have made sense. Similarly, it might have spotted flaws from an engineering perspective that I don't think this tool is able to spot. But to the degree that it relied on what was stated in the papers, like actual sentences and written explanations in the papers, I think it did a very good job of finding all that information fairly quickly and turning it into some very nice answers to these questions. So pretty impressive. Just be cautious about when you're talking to it or listening to what it says that it is a language model and it's not a real engineer, and so I imagine that it will say some things sometimes that are not quite correct. But I would expect that from lots of engineers as well. So pretty damn good tool, and I'm quite impressed with it. Yeah, I think this technology is coming a long way, and I would not be surprised if in a year or two it's starting to understand technology as well at a deeper level. It already seems to be kind of understanding it, but it's making mistakes. So I feel like it's a bit of an illusion right now, but it's getting awfully close to it not being an illusion. All right, well, that's all I have. I think this tool is definitely worth checking out, and especially if you're not familiar with the material, it's probably going to help you very rapidly learn some material. So, very good, Google. I'm quite impressed.